So this is Conceptual Chemistry, Chapter 9, Section 7. Catalysts speed up the destruction of stratospheric ozone. So catalysts are things that will speed up your reaction rate. So a catalyst is any substance that increases the rate of a chemical reaction by lowering the activation energy. It's not the same thing as increasing your temperature. A catalyst is an actual physical thing that you will add in on the reactant side, and it will lower the activation energy. Catalysts do not get used up. So you have the same amount of catalyst after the reaction as you did before the reaction. So an example of this would be that catalysts actually speed up the destruction of ozone in our stratosphere. So they cause in our stratosphere, we have oxygen molecules plus UV radiation is going to form ozone. And we need that ozone in our atmosphere because the ozone is part of what protects us from the ultraviolet radiation. The ultraviolet radiation plus ozone generates more ozone plus heat. So ozone reactions are what stop about 95% of ultraviolet rays from reaching the Earth's surface. You're in much more danger of a sunburn now than you were 100 years ago because our ozone layer is not as thick. And so we don't have as much protection from the ultraviolet rays coming from the sun as we used to have. Now, back in the 1970s, we became aware that chlorofluorocarbons were destroying our ozone layer. And we'll get into that in just a moment. So, UV rays, that's ultraviolet rays, break apart chlorofluorocarbons, that's CFCs, and produce free chlorine atoms, which speed up the rate at which ozone molecules are used up or destroyed. They become oxygen molecules. So here you can see two ozone molecules, and there's an activation energy here, that's this hump. And then you can see three oxygen molecules. There's 6 oxygen atoms on the left side. There's 6 oxygen atoms on the right side. So ozone does tend to become oxygen molecules. And you can see that the oxygen molecules are at a lower energy level. So that's a favored reaction to happen. When we add chlorine to the mix, and here you can see chlorine in green here on the on top of the yields arrow, that is to indicate that chlorine is a catalyst. When we add chlorine into this, that chlorine it lowers the activation energy. You can see the activation energy on this slide was much higher. It lowers the activation energy so that it's easier for the ozone molecules to become oxygen molecules. And this point we're supposed to do a slide, so let me see if I can get this to work. I think I can make this happen. Let me go. Okay, here we go. So this is our chlorine molecule, is the thing that's in green here, and it is sliding around and connecting with the oxygen molecules. Did you see what happened there? You'll see it happen again. This is an ozone molecule. It connects with the chlorine, and then it breaks it apart, and that chlorine atom is still there. The chlorine doesn't get used up. So let me play this for you again. So that's an ozone molecule that's in red. The chlorine grabs one of the oxygens off of it, and then it knocks another oxygen free off of another ozone molecule, and then we have 3 oxygens sitting there. So this is how chlorine speeds up the change from ozone to oxygen, because the chlorine has a really easy time breaking apart the ozone molecules. Okay, so I'm going to close that. Hopefully that actually recorded for you. So this is how the actual thing works. We have our chlorine atom here on the left, and we have an ozone molecule next to it. We're going to react those together. When we react them together, what we form is chlorine monoxide and an oxygen molecule. Now, that chlorine monoxide runs into another ozone molecule, and that breaks the chlorine atom free, and we have 2 oxygen molecules. So you can see here we started with a chlorine and an ozone. We ended up with chlorine monoxide and an oxygen. And then that chlorine monoxide reacted with another ozone to break the chlorine free, basically, and produce 2 oxygen molecules. So we started with 1 chlorine and an ozone, And when we added one more ozone to it, we ended up with a chlorine and 3 oxygen molecules. So we started with a chlorine atom and we ended with a chlorine atom. The chlorine did not get used up. So this is the full reaction happening here. Chlorine plus ozone produces chlorine monoxide plus oxygen. The chlorine monoxide reacts with another ozone to produce a chlorine and 2 oxygens. And again, we started with a chlorine atom and we ended with a chlorine atom. Okay, whoops. So that's why we have this double bump here. It's because there's 2 different reactions happening here. We have that first bump is for this first reaction up here at the top. The second bump is for the second reaction here at the bottom. And so that's why we have 2 different activation energies here. So we start off with 2 ozone molecules, throw in a chlorine atom, and we're going to end up with a chlorine and 3 oxygen molecules. The chlorine does not get used up. The chlorine ends up going on its merry way and causing this to keep happening again and again and again. So the chlorine reaction has a lower activation energy, so it makes the conversion from ozone to oxygen happen more readily. It happens much faster. But we have the same amount of chlorine at the end that we had at the beginning. So a single chlorine atom in the atmosphere can catalyze the formation of 100,000 ozone molecules to oxygen molecules in just 1 to 2 years. It takes about 1 to 2 years for that chlorine atom to finally get grabbed by something else where it's no longer out there to be converting ozone to oxygen. So our whole chlorofluorocarbons, CFCs, were once commonly used as refrigerants. These are 2 different CFCs here. The one on the left is CFC11 and the one on the right is CFC12. These were commonly used as refrigerants like in your air conditioning system. But it was recognized that these compounds were a major source of chlorine atoms in the stratosphere. And we don't want extra chlorine atoms floating out there in the stratosphere because that causes the faster conversion from ozone to oxygen, and we need that thick ozone layer because that ozone layer is what protects us from the UV radiation, ultraviolet radiation. So this shows us the concentration of ozone or chlorine monoxide molecules per billion air molecules. So latitude is, when you look at a globe, the latitudes are the horizontal lines. So how close you are or how far you are from the North or South Pole would be the latitude. So you can see this is our concentration of ozone. And this is our concentration of chlorine monoxide. And as the concentration of chlorine monoxide goes up, the concentration of ozone goes down. So where there's low chlorine monoxide, there's high ozone. Where there's high chlorine monoxide, there's low ozone. And we need that ozone layer. So this is a graphical image of the Earth. So you're looking at the South Pole here. So this is the South Pole here, and you can see that we have a hole in our ozone layer here. And our concentration of chlorine monoxide is very high here. And then in the picture next to it is our concentration of ozone, and our concentration of ozone is very low in that same area. Okay, so while catalysts can have some negative effects, chemists have been trying to use catalysts for positive purposes for a long time. That's why we have catalytic converters. We take things in from the engine, and you can see we have nitrogen monoxide and carbon monoxide and a hydrocarbon. And then out to the atmosphere, we have water, oxygen, nitrogen, and carbon dioxide. So we have reactions happening inside of these catalytic converters. And that is all for Chapter 9, Section 7, How Chemicals React. This one was about catalysts. A catalyst is something that once you start it going, it's going to cause reactions to happen more easily. Your catalyst does not get used up. You had the same amount of catalyst at the end as you had at the beginning. And that's why catalyst can be so very destructive. Now, at this point, I want to see if I can show you some of these other animations that I tried to show before and I didn't know how to make it happen. So let me grab this up really quick. I wanted to show you the wrong orientation. This was from the last section. Here's two molecules colliding from the wrong orientation. See, if they aren't lined up parallel to each other, they can't combine with each other. And now I'll show you what it looks like when they are just right. So when they're just right, you can see they hit together and they immediately pair off. They hit together and they pair off. Now, if they're not moving fast enough, they're just going to bounce off of each other. No reaction happens. And here we'll see it again. They hit and nothing happened. No chemistry. Okay, so that is all. And I will end this one.